everyone. So welcome to our presentation for our thesis with Luba. So our thesis is about using a model predictive controller based controller to control the steering of the car using only the path in local frame. Um, so First of all, I would briefly introduce the motivation for why we chose this type of controller and a bit of background behind the theory, model predictive controller. Then Luba will continue with presenting the theory of the model predictive controller, which we will usually say as MPC for short. Then after that, I would present the steps in our methodology to validate if this controller would work. So basically, our thesis would be about simulation to simulate the performance of the controller in simulation. Then we would present the results in the simulation and then we conclude our presentation with some conclusions and discussion of any possible future work. So I guess I can skip the first part about our project. So as most of you know from last year and also in this year, we are using the endpoint approach to control the car. And the idea is that we choose a point in the middle of on the middle path, and then aim the car so that the car would be perfectly aligned with that point. And our motivation is that if we could use an NPC controller so that the car could be able to predict how it would move only based on how it sees the road in its local frame, then perhaps it could come up with slightly better steering controller. And the reason why we emphasize the word local frame in our thesis is because in most path tracking problems that are related to NPC, then it is usually the case that we need to know the position of the thing that we want to control in a global frame, or in other words, we need to have a good global localization. But this is not always the case, either because we don't have global localization, or if the global localization, like maybe GPS, is not too accurate or too fast enough. So our thesis would aim to clarify this question, which is if it's possible to. So from that motivation, we have come up with two research questions. One is that if it's possible to use this MPC steering controller with only the local path information, and how would it perform? And the second research question would be, can it run fast enough to be implemented in real life? Or in real time, sorry. And so this is a short summary of our problem in the thesis. It's a path tracking problem where we are given a local path, and we would have to steer the car so that it can track the path perfectly using only steering angle.
Right. So I'll just give a brief introduction to what model predictive control is, because I assume most idea is that it's a control system that predicts how the system will evolve within a certain time frame. So in this figure here, on the left-hand side of the y-axis, we have the past, and these are points that we have measured that have actually happened. And on the right-hand side, we have the future of the system, which is predicted based on a system model. So the idea is that at every time step, every time this system is updated, we make a prediction on how the system will change within this time frame. So n steps in this case, and then we use then we calculate the best control input based on a certain specific cost function, and we use the first input that is calculated for this whole time frame, and then we redo this in the next time frame again. And this is really nice because then the system is always adjusting to the current specific state of the system, but it makes it a bit more heavy because you are redoing this calculation at every time step, and you're predicting way longer than you're actually updating. But the good thing about this kind of approach is that you can account for constraints in the system because you're predicting how the system will evolve. So this is a typical formulation of an MPC problem. There is a cost function that is subject to some certain things like how the system evolves and constraints on the states or constraints on the inputs to the control system. And you have a typical cost function here which depends on the states and the inputs. So these matrices Q and R can be tuned to basically modify how the behavior or the wanted behavior of the controller, like either we punish state errors more, or we punish input errors more, or input cost more. And this kind of optimization problem can be solved by quadratic programming. So this has to be formulated in a specific way, and is usually more cost efficient to also linearize the system and then solve it instead of using a nonlinear model. So advantages, as I said, you can take into account state constraints and input constraints. You have a model of the system, which is a bit of a double-edged sword in this case, I think. And you have multivariable interaction, so you can have coupled control for multiple states and multiple inputs to the system. Disadvantages is it needs a fairly correct model. So if your model is super bad and it doesn't capture the dynamics of the actual system at all, then the control will be bad. It's hard to formulate the problem sometimes, and it's computationally heavy. And in the case where you have a bad model, you won't have a feasible problem which can actually solve this controls problem.
So as I have presented before, our thesis is only restricted to simulation. And we run the simulation in MATLAB only. So in order to put somewhat accurately model what is going on in real life, so we need first is a model of the car. It means it's like a dynamic model that describes how the forces in the car would interact with each other and how it would make the car move. Then, secondly, we also need to model the car's perception and path planning. This is not really the emphasis on in our thesis, so we will not talk too much about it. Then we will design an MPC steering controller using only the path perceived by the car in its local frame. Then we run the simulation, and we in several test scenarios. Then we log the data from the simulation of the things that we are interested in, such as the car's global position, the steering angle, or maybe its lateral velocity. And then from those collected data, we would analyze and make conclusions. So this is a graphical representation of the structure of the simulation. We set the sampling time in the simulation to 10 milliseconds. It could be set lower so that we would achieve a more accurate one, but we think that 10 milliseconds is enough. And because the car's dynamic model are all differential equations, so we need to somehow approximate those differential equations in discrete system, and for that we use a method called Runge-Kutta. It's a pretty standard way to simulate differential equations in simulation. And so, in short, from the driver model would choose for the perception would perceive the cones. They send the cones to the driver model, where they construct their local path. From that local path, or that local path would be then passed to two separate controller. The MPC lateral control will control the steering, and the longitudinal control will control the torque request. And our focus would lie on the lateral MPC controller. The longitudinal controller will not be covered in this report, but basically its job is to make sure that the car would have to travel at a constant set speed, because the lateral MPC controller would require the longitudinal speed to be constant. And from that on, and the lateral controller would calculate the most optimal steering angle that results in the car tracking the path with the least lateral deviation. And we run with the calculated steering angle and the torque. We supply those two control inputs to the plan model that it run with the dynamic model of the car to get the next states of the car in the next time step, and then we repeat the cycle again.
So this will be our simulation model for the vehicle, and I won't go into details here, but it's a dynamic single track model with the assumption that longitudinal speed is non-zero and we have no load transfer. This model can definitely be made more accurate, and there is a whole thing with actually validating how accurate this is in relation to the real system, but it captures the most important dynamics of the vehicle movement, at least. So we basically have some equations of motions that we can get from force balance of the car, some lateral tire forces, side slip angles, wheel speed acceleration and roll friction, longitudinal wheel slip, and longitudinal wheel force with the road. But as I said, it's not really too interesting for this. We have a simulation model. It's more accurate than the assumption made by the controller, essentially.
So here's a bit recap of our currently implemented endpoint on the car. Given a middle path, it will choose a point on the path that is at a certain distance away from the car. That distance would depend on the current velocity of the car times a tunable parameter called the preview time. So basically, the faster the car moves, or the further it sees, then the further away the endpoint would be from the car. and it would calculate this error angle between where the car is currently facing and where the endpoint is with respect to the car, and then it used that heading error as the input to a PID controller, which directly controls the steering. So we propose a different approach, and it's not to it is different. We don't choose a single point to aim at, but instead we choose a section of the middle path. It could be the whole path, or it could just be just a part of the path. Basically, the idea is that we would use this middle path in the local frame as a reference signal for the MPC, and the MPC whose job is the MPC's job is to calculate the most optimal steering angle that would allow the car to perfectly track this middle path. In our case, the middle path would be a collection of coordinates that is relative to the car's frame, and in order to create a good reference path for the MPC, then we assume that the car is traveling at constant speed, and that from that constant speed and given a sampling time, we know how much we know the distance that the car would travel per sampling time, and then we divide this middle path into a number of segments that each segment would have the size of the distance covered by the car in one sampling time. And then for the MPC steering, there is a tunable parameter, it's called the prediction horizon, that tells how much into the future the MPC would predict the car. And then we assume that in the most optimal situation, there would be a steering angle that allows the car to perfectly track the local path. So we would only choose the number of path or the part of the middle path that is equal to the prediction horizon. This is to prevent the case when the car is traveling kind of slow and the path and the middle path is long, so that it would result in a very big prediction horizon, which would make the computational time really heavy. So after we get a valid reference local path, we would formulate the steering problem into a quadratic programming problem. And then in MATLAB, we use a command quadro to calculate the most optimal control input position steering angle. And so this is the structure of the lateral controller. This is where we get the reference path from the middle path. This is where we construct the model of the controller. So previously we mentioned that we use a single track model for simulation, but the single track, but for the controller only, the controller also needs a model. But because it also has to calculate or to run this MPC steering fast enough. So in order to ensure that we only chose a simple kinematic model. Basically, this model would include 3 states: the XY coordinate of the car, and the heading angle of the car, and it only has one control input, which is the steering angle. This we chose this kinematic model because we assume that if we don't drive the car too fast, then the lateral deviation that in the bicycle, or the lateral velocity in the bicycle model is not too large, and the kinematic model would be enough to capture the dynamics of the bicycle model somehow. For quadratic programming, it is required that the model has to be linear. The chosen kinematic model is nonlinear. It is simple, but it's still nonlinear, so we need to linearize it. So every update time when we measure the current states of the car, we would linearize the kinematic model around that state to get a linearized model. So once we have the linearized model, we feed it to this block, which is where we formulate the quadratic programming problem. We construct a cost function that is a function of the lateral of the not the lateral, but there is a cost function of the error between the current states of the car and the reference signal. The reference signal in this case would be x, y, and the heading of the local path. And the cost function is also a function of the control input, which is steering. We also impose a constraint on the steering angles, because the car cannot steer. There's a limited range of how much the car can steer, so we have to impose a constraint on the steering angle so that it can it is like what it is in the real car. Then so after that, the quadproc command in MATLAB would calculate an optimal steering angle, and then we apply the steering angle to the plan.
You're a little bit running out of time.
Yeah, we will hurry up this last part. So this is result of a simple lane change test. So the car starts at the top left corner, 2 meters in the lateral direction from the reference path, and then we apply the MPC steering system based on this reference path. And as you can see, it can minimize this error. It can follow the x coordinates perfectly, then can minimize the error in the y coordinate well, and it can minimize the heading error while keeping the steering angle. I know it's a bit hard to see here, but keeping the steering angle within the input bounds, basically within minus 25 degrees. So it works well here, and our other case is in the full track, and we had a bit less good results here actually. It's super hard to see here, but the results from this is basically that the aim point was performing better when compared here. They were running at the same constant speed over the whole track, and the aim point was performing better, and the NPC was performing better by looking at less of the track for some reason, which is a bit unexpected and does not really match with our previous results. So there is definitely some more work to be done in that area. But it's basically the results. It can minimize the error and it follows the reference path. But in this case, with the full track, it's a bit off center at all times for some reason. Yeah. So basically, it can follow a reference path. In the case of us, just basically a step response as in the first test, and it's actually really good. In the case of the full track, it was a bit weird, and as I said, the shorter the horizon, the better tracking in that case, which is a bit confusing and not as it should be. Um, but we also had a question in the beginning of this, where if the real-time application of this would be possible, and in this case, since we're using such a simple model, it takes only 15 to 20 milliseconds to update with a horizon of 40 steps done, which is quite fast actually for MATLAB, and it would possibly or most probably be more faster when using a compiled language like C++ or something other than MATLAB. Yeah.
So we think that we would. There's still a lot more, to improve our thesis, since we have kind of limited time to actually work on it. Some of the things that I think are important to do is to add constraints, because right now we only have a constraint in the current in the steering angle. What we aim at is that we could somehow come up with another model where we could apply a constraint on the lateral deviation. So that would kind of secure that the car would never go out of bound of the track. So that requires us to change the model of the controller. Also, there is a thing that model predictive controller assumes is that the reference model would have to be the same every time we run the MPC, which is not really the case in this case, because from the car's perspective, whenever it moves to a new position, then the local path would look slightly different. Eventually, we think, we could guess, and it also shows in the simulation, that once the car is able to stabilize itself in the middle path, then and when it is able to stabilize, then the middle path would not change too much. But perhaps for future work, we would have to somehow take also the change of local path into consideration. And last but not least, we need to verify this by experiments in real life.
Very good.
So,
So
thank
then,
you.
very good. So then we open up for the opponents now.
Yeah. Me? Okay. First, I have a question. Like, how did you come up with the idea of using this model? Do you have like references from other teams that they are using this kind of model? Or?
For the car, the simulation model, you mean?
Yeah.
Yeah. We are taking some parts from last year and some parts from other research in this area, but it's definitely, as I said, like this simulation model can definitely be improved. But the main idea here was just to capture at least the most important dynamics of the car, and that is that it has some kind of slip and acceleration and stuff like that. But this is something that also is hard to verify. Like, even if we try to use data from real life, since that is noisy, it's a whole work just to verify that. So there's no good way of having a perfect model and perfect validation of that model in this case, without putting a lot of effort into that part. So the idea is just to capture the most important dynamics based on other research and the previous year.
Yeah, that was one of my other questions, like how do you actually verify that it's the perfect one? Because you said like, yeah, it's good because you can have a perfect model, but I was wondering how you verify it, but it seems to be very hard yet. But did you hear of any other teams that are using the same methods? Or?
I guess ETH Zurich, they probably have, they also use controller for an MPC controller, some kind. According to my research, the difference though is that they have a good global localization, I think, so they know the position of the car in global frame.
Okay.
I think in their controller, most likely they've also coupled the longitudinal control with MPC.
Yeah.
There are definitely benefits from doing that, and there are also complications from doing that. But most likely they would use one MPC controller that controls both the steering angle and the torque of the motors. But there are definitely other teams that are using a similar approach, but not maybe only for the steering.
Okay. You were comparing the last year's endpoint and your method, NPC. Is it like, did I understand that right, that you are basically also looking for the middle of the track, like in both cases? It's like from a racing point of view, how easily would it be possible to implement something that goes also like the cutting the corners and like it's already very improved, I would say, in that case. But did you look into that? Did you?
I looked a bit into that, and there are definitely ways, but the less information you have about the whole system, the harder it becomes. When you only have the local path, you really don't know what's coming up. Then it's hard to cut the corner, because then you might try to cut the corner and then you realize halfway that, okay, your orientation is super bad because there's this upcoming turn, or the turn is not really evolving as you expected it to. That's why we just chose the middle path, because only based on local frame and no global map, then it's kind of
okay, so
hard.
that could be a better case then for if you have the whole picture, like.
Yeah, then there are definitely multiple ways of doing that.
Okay.
And based on a optimal control problem where you try to minimize your track time based on your model. So there are definitely ways, but it's hard in the local frame, so we didn't really, that would be like one thesis by itself, just trying to figure that out.
Yeah, okay, that's what I want to see, like how hard it is. At one point you said something about, I'm not sure where it was the longitudinal speed is not zero, it's assumed in this kind of model.
Yeah.
What are you doing if it's zero?
And if it's zero, then it so if I, or maybe, so basically the bicycle model that we use for simulation assumes that the velocity is non-zero, because in the equations the velocity is in the denominator. So if it is zero, then you get it divided by zero.
Yeah.
So it is a shortcoming. This is a shortcoming of this kind of model, is that it does not describe the dynamics accurately at low speed.
So there could definitely be ways to fix that, like, but it's also the fact that we were trying to capture dynamics at a bit higher speed than like 1 meter per second or lower. So that's basically our assumption, that we're always moving in that case, because we don't really care too much about when we're standing still.
Okay, yeah, no, it's all makes okay.
Yeah. I had one question. Is the control input discrete?
Yes.
Yes. As I understand, control input is like an angle, essentially, steering angle, yeah? Is it really discrete?
No, it wouldn't be discrete in real life, but I think it's also a bit of a shortcoming in our model here, is that the steering input is assumed to be applied immediately.
Yeah.
And you can definitely constrain how fast the steering angle can change also, which is something we try to implement in the model in a good way. But within those time steps, every time we evaluate this control problem, the steering angle is constant, basically. So you have, every time you solve the optimization problem, you have a constant steering input until the next time you solve it, and you get a new constant, discrete steering input.
Okay. And that was my, I guess, second question is, there was a mention of, if you return back to graph thing, that you're predicting, as far as horizon goes, right? You're predicting the next control output,
Yeah.
right? Is it done also by the model itself? Like
you mean-
it's based on what you currently get. So this light blue thing,
Yeah.
prediction horizon. What is that essentially? Is that predicted output of your MPC for the future steps?
Yeah, that's basically how many times you estimate the next state, basically.
Until you reach the goal you're
Yeah, so in this case, we would basically have a certain length, or we have a length of this.
like 10 or 20 then.
Yeah, and then we would evaluate like 40 steps. Like, if we tried to follow this specific road reference,
Yeah.
how would our system move within that specific path?
So essentially, for the current point, it's setting the output is assuming that it would change later on
Yeah.
to reach the endpoint. Okay. And I didn't understood why you have to linearize the model. As I understand, the more complex model is, the more dangerous it is to linearize that and not to lose the model specifics.
Yeah, that's you don't have to linearize the model to solve the problem. You could have a nonlinear model, but that increases the computation time by so
Yeah.
much
Yes.
that it's not really feasible in real time. So one assumption is basically that you linearize it around that specific current state, which would be the one you're measured at that time point, and you're assuming that within that prediction horizon the system dynamics don't have time to change too much. But it's also it doesn't matter too much, because even if at the end of the prediction horizon maybe you're not really as accurate as in the beginning, but then you redo the whole thing in the next measured state. So then at every measured state it's accurate within the first prediction steps, and then it gets less and less accurate
Okay.
as the more you go. So then there's also a balance, like how far should you estimate, because you know that if you estimate too far, it's not going to be accurate if you linearize the model. But that's also tuning part of this controller then.
But so do you think that you mentioned as the disadvantages for the MPC method that the less accurate the model is, the more problematic this whole thing is, and understand that the model, as I understand, the model is a dynamical model of physical car, like how it moves and behaves. Do you think it's realistic to model such a complex system for this to be feasible in real life?
There have been research, actually a lot of research, to whether or not a kinematic model is enough, like using a less accurate model. And it's kind of also at the speeds we're running at, as it's accurate enough based on previous research, but you could definitely use a more accurate model and you would get better results, but you will also increase the computation time. So it's, and since you're also linearizing at every time step, it's a question about how much is that extra overhead on a better model worth. It's not really easy to answer.
Yes. Yeah, I don't have any more questions.
Do you have any other questions?